Okay, so before we start with the last lecture, I will ask you to join me to send the staff people in CIMAC who is helping us to organize the conference. So here we have Lupita and Guillermo. Who are the ones that are, well, you have seen them, they are working directly with us, but there are also other people that we have seen less, that they are changed of a lot of things, like transportation, so also thank you to the drivers, and also the recordings and other many things, so Maria Isabel is there also representing these people, so thank you very much. Okay, and now it's an honor to introduce Claudia Spolini's last talk on the module of differentials. So Claudia, when you're ready.
So thank you to have come the long way until the last talk. Hopefully we'll enjoy the end of it. And so I put in the first board something we saw last time, so it can be clear because we'll use it the whole time this class. So A is Noetherian, and remember that R is an A algebra, essentially a finite type. And we defined the Kähler different already several lectures ago, and that is simply the zero fitting of the modulo differential, or if you want, the maximal minor of the Jacobian matrix, the n by n minor of the Jacobian matrix. And now we want to define the Noether different, and to define the Noether different, we use the third definition of the modulo differential. We look at enveloping algebra, we map it into R via multiplication, and the kernel is given by the diagonal idea. And the annihilator of that kernel, the image of the annihilator of that kernel, so if you want, is also R times these things, times this annihilator, okay? So the annihilator of this kernel is the Noether different, okay? And I wanted to remind again that the modulo differential can be obtained from the diagonal ideal, tensoring over RE with R, and this is D over D square, okay? Last time we already saw a relation between these two different, okay, and I talked about the different property and so on, and we saw that the Kähler is contained in the Noether, and the Noether is contained in the radical of the Kähler. So up to radical they are the same, and that's why they define, both of them define the ramification loci, okay? But with a different scheme structure. And now the theorem we start today is when does equality hold? And we prove that if this extension is locally flat complete intersection, okay, so this is a complete intersection after you localize, and this is flat, then you get actual equality. So let me sketch this proof. I don't go complete in the detail, but all detail are in the notes. I just want to sketch and tell you the idea. There is a problem that you have to do that is similar to this in today. So you can think about it again. So remember that everything localizes. The different localizes, because the modulo differential localizes. Flatness localizes, and this actually is locally. So we can localize everything, and then we can assume that R can be simply written as A with a bunch of variables, the n that you find here, that's n we need, localize at W, divide F1, Fg, where this one are, and this is very important, are irregular sequence. That's the fact that it's a complete intersection. So this is how our R looks like, okay? And now we want to write Re, the enveloping algebra, but Re is R tensor R over A. So what do? You just need two copies of R. So one copy you could think as a variable x's, and another copy as the variable y. So I can write it as R tensor A, this is the x copies, with A, and now I put new variable for the second copy, okay, over F1 of y, and so on, Fg of y. And this is obviously localized to wy if you want. Okay? So this is just a second copy of R. And to remember that is a second copy, I put different variable. Now this is the same, if you want, as R, let me call it R, because I tensor over y1, yn, localize obviously this wy, okay? And then f1 y, let me write it well, f1 y, comma, comma, fgy, okay? And call this ring S. Okay? Now, what do we see right away? Okay? First of all, you can notice immediately, because we assume that this thing is flat, that you still have that S is flat over A, y, y1, y, and W. So this F1, F1G were a regular sequence in R, they're obviously a regular sequence here, because of flatness. So this is still a regular sequence. Okay? So this is our situation. We have this regular sequence and this ring S now. Okay? And now, how can we think in this way when we have this, we describe RE this way? What is D? How does D look like? But it's not difficult to see how D look like. Just think about how you get R from S. R, so let me write it actually in orange so it's clear. R is simply S. And how do I get R from S? What do I have to do? But I have to make the x equal y. If I make the x equal y, I get back R. So this is simply the idea y1 minus, and now let me call this the images, small x's of this x's inside R, yn minus xn. And these are the images of the big x's inside R. So this is going to be simply your R. And if you think that R is, or get it, putting y equal x, because then you get the same R, and you tensor over A, so you get R, then it's clear, two things are clear right away when you write this. First of all, you get immediately that from this, the ideal generated by the f's evaluated at y, they are contained in this y minus x's. Why? Because when I go in R, I evaluate this f's at x when I go to R. But in R, the f's are 0 when they are evaluated at x. So this is contained here, because when I go modulo this becomes 0. Okay? So this is the first important observation. The second important observation is that we can get D from here right away, because D is the kernel of this multiplication. So D is simply this ideal, y minus the x's, modulo obviously fy, because it's an ideal inside S. Okay? Because it's the kernel. Okay, that's how you get R. Okay, so these two observations are very important. And what do they tell us? Remember, I want to compare this with this. So I want to compute the annihilator. So I need to write the annihilator. But now I can write the annihilator here, because I have a nice expression of D. I can write what the annihilator. This is like an ideal divided an ideal, J over I. What is the annihilator? Let's write the annihilator immediately from here. The annihilator of over RE of D, but it's simply, you have to find the stuff that from this ideal inside here. So it's f of y, okay, colon y minus x over f of y. Because you have to find the stuff of RE that sends this one inside here, and then will be 0. The ideal, if you have J over I, the annihilator is I colon J over I, okay? So this is simply the annihilator. This is done in RE, okay? So that's what we get immediately. Clear? Okay, not finished. The fact that this is contained here tells me that I can write this in terms of this. And I have a transition matrix. So I can write f of y, okay, as this y. Think of it as a vector times a matrix. I'm going to call it phi, okay? And what is the size of this matrix? But of this one I have n, of this I have g. So it's going to be an n times g matrix. Because you have to take n times this, so an n times g matrix, with entries in S. Okay, so far so good? Everybody understood what we have? Okay, good. Now, so the point is that these two are both regular sequences. Okay? All right? This is a regular sequence of length g. This is a regular sequence of length n. This regular sequence of length g is containing a regular sequence of length n. What does this tell you about n and g? Guys, who is bigger? N, because this is containing the other. So this tells you immediately that n is bigger than equal than g. But now when I do this column, the grade of this ideal of D, okay, if this is strictly larger, the grade of this ideal is positive, so its annihilator is 0. So if n is larger than g, the annihilator is 0. Okay? And if n is equal g, then you have a regular sequence inside another, and this column is called a Norcott ideal. And it can be computed with linkage. And it's simply given, this becomes a g by g matrix, and it's simply the determinant of this. So in general, I can write this as f of y, will always be in the column, comma, I, the maximal minor of this, because if n is bigger than g, this will be 0, which is exactly what it should be, okay, modulo f of y. Okay? So this is an Norcott ideal. Generated by the determinant. Okay? And obviously, f of y. If you have not seen that, this is very, very important. Do it as an exercise. If you have never seen Norcott ideal, they are very interesting. They are exactly the linkage, but of a regular sequence inside another. Okay? And I put an exercise for you to do. So in general, we have, this tells us that this annihilator is simply this. So what if I need to look at this image in R? If you look at the image in R, this will just be generated by the image of this guy. So what I get from here immediately is that my mu of the annihilator, so my d of Noether different, which is mu of the annihilator, so simply the image when you throw it in R, is simply given by n of phi, times R. So I have to take this matrix, throw it to phi, to R, so the entries are in S, look at the image in R, and then multiply by R. Okay? Because that's the generator. Is this clear? So this ideal, you look at the image in R. Okay, so far so good. Now we want to check that this guy is this guy. Oh, but they're very similar. They're maximal minor of a matrix. So what do we have to show? We have to show that this phi bar is the presentation matrix of omega. So we have to show that phi bar is a presentation matrix of the modular differential. So how do we compute a presentation matrix? I can compute it via a presentation matrix of D and then tensoring, okay? And I can get a presentation matrix of D because D is this nice thing. So it's easy to write a presentation matrix of D. So let me do that. I don't know if you ever did this, but this is a nice, very nice exercise. So D, in theory, is generated by these guys, and there are n of them. So I need S to the n, okay? And then which matrix I need to present it? But the syzygy are given by what? Are given exactly by the stuff that sends f of y inside here, the transition matrix, which is our matrix phi, okay? And then the syzygy matrix of this, but this is a regular sequence. So it's the second syzygy in the Koszul complex. So let me call it script k to remind you that this just comes from the Koszul complex, okay? So it's just the second, the syzygy in the Koszul complex, because that is a regular sequence of y minus x, okay? And now, what we get from here immediately? I could call it delta or delta k, maybe delta k because it reminds that it's from the Koszul complex, okay? And so this one is exactly 2 copies of Sn, you know how to do the Koszul complex, direct sum Sg, because this is the size of this matrix, okay? N times G. And this matrix presents this guy. Now, I want to get a presentation of omega. I have to tensor with the enveloping algebra, tensor with R over the enveloping algebra. And if I tensor, here I get exactly R to the N. Here I get exactly omega, okay? And what do I get here? But this guy is 0, okay? Because the y are equal to the x's. So I get 0, and here I get phi bar. Okay? So this tells me that phi bar presents omega, and this indeed is equal to that. Okay? That's it. So this is the proof of the quality. And now that we have seen the quality, I want to go and explore and define the last different. And this different is more complicated. As I said, there's a longer history, but it's a little bit more complicated. So let me start with that different, okay? And let me tell you what are my... You're going to practice, because you have homework 4 in set 4 is like this. So you're going to do this proof, hopefully. Okay, let me leave. The first thing I need to leave, so I'll have to use less Blackboard because I want all this out, because we'll need it. Because eventually we want to compare all different, okay? So to introduce the Dedekind different, I need to introduce the complementary module, okay? Yes? No.
Are there any conditions under which we have one equality, or we have, is it unknown about that second inclusion?
Oh.
That there's an equality? So we only.
So we know we don't know in general, but there are cases when we know that this is radical. You're asking when it's radical. Yes, yes. Remember, though, that this condition in the board is only sufficient, is not necessary. Okay? And I'll talk about this. I'll say just a little bit after, but it's only, sufficient. So if this happens, there is an equality. Otherwise, we don't know. Okay? So now let me show you, introduce the complementary module and the Dedekind different. So first of all, the situation is going to be different. Okay? I need more assumption. So what I'm going to assume now is that not just that this is essentially a finite type, usually you always need at least that this is a finite extension. I'm going to assume even more. I'm going to assume that this is another normalization of R, just to make it simpler. It's not very far from what we need, because you need so many assumptions on A, and this to be finite, that at the end is not very far. So let me assume that is another one. I mean, it's more. In general, you need less. In general, you just need this to be a Noetherian domain, okay, and this to be finite. And then you need also information. You need R to be A torsion free, in general, and then you need R to be reduced and equidimensional. So you have a lot of assumption in any case. And what do I assume now? I assume another normalization, which gives me the torsion freeness and lots of other stuff. But I also assume that, and obviously it gives me that A is a Noetherian domain, I assume that R is reduced, equidimensional, and then an assumption more, which is complete. You wouldn't need this, but I just want to make it easier, okay? I want to make it easier, so I assume all this, okay? Though remember, it's quite restrictive anyway, but now you could ask, you never defined the modulo differential under completion. But in this case, because the extension is finite, it's the same as the one we're used to. So there is no problem, because the extension is finite. And now, what does this mean? This means that A is a power series in a bunch of variables, okay? This is, remember, it has the same dimension of R. So this is the dimension of A equal the dimension of R, since it's another normalization. And this Y1, YD are a system of parameter for R, okay? And R is simply A when you have to add another bunch of variables. Let me call it Z1, Zn, okay? Modulo an ideal. Okay? M, we call it M. Okay? Oh, no, because they have the same dimension. Yeah, M. And the point is that the height of this has to be n. So the height of this guy is n. Because remember, this has to have the same dimension as R. Okay? So this is the situation. And now we are going to look, so a very simple situation. And now we are going to look at the quotient ring of these two guys. So K is the quotient field of A, and is obviously a field, okay? This is a field. Now you are looking at the, I put it here, quotient ring of R, okay? And the quotient ring of R is not a field, but since R is reduced, is a finite product of fields. So this guy is going to be the product for 1 to, I didn't use S, good, of Li, which are, these are fields, okay? And now because of our assumption, these Li are simply the quotient of R over Pi, where Pi are the minimal prime of R. R is equidimensional and so on. So in particular, what you get immediately, because this guy have the same dimension, this is another normalization, is that the A is contained in a Ri in this R over Pi, okay? All right? So, which implies K is contained in a Li. And furthermore, this is a separable finite algebraic extension, because this is finite, R over A. They have the same dimension, so it's even algebraic, everything. Okay, it's a beautiful extension. Okay? So in particular, since K is contained in Li, K is contained in the product. So K is going to be contained here, in this quotient. But now, I can also consider this guy. I can take R, and I can tensor it over A with K. Okay? And I get equality. Okay? So this is very important. So this, I call this L, this quotient. So L is K tensor R, and is contained in K. I mean, it contains K. So this is your situation. Now, why do I do all this? Okay? I do all this because I want to consider certain things. I need to consider the homomorphism of L over K. And I want to see what these homomorphisms are, okay, of Z over K. And first, to consider that, I consider the homomorphism, since L is just the product of Li, the homomorphism of the Li against K. And these are much easier. Why? Because these obviously are a Lie vector space, one-dimensional, so they are just generated by one thing. And what is that one thing? But this is a separable extension, a finite. This is a trace. So this is generated by the trace of a Lie over K. Okay? So that we know. But now, because of that, you can just define a trace map. This is different from 0 because it's separable, okay? So you can define a trace map at this level. Just take the trace map, okay? You define it exactly like you would imagine to define it from R to K. Remember, this is a product of field. So the trace on x1, how many I had? S. xs is simply the sum of the trace of the xi. You know, Li over K. Okay? And this is also different from 0 because these are different from 0. So this has to be generated by that because it's also cyclic. So it's the trace of L over K, so define, this is the trace of L over K, times L, which is obviously homomorphic to L. Okay? And now inside this guy, I want to find somebody else. So let's see what we do. Okay? How do I find somebody else inside that guy? So this, remember, okay, is equal by what we wrote here. Look at what I wrote. L is K tensor R. So I can write this as hom over K of K tensor R over A, okay, with K. Right? But now I can take out the K. And this is K tensor, okay, over A, of which hom? I took out the K, so it's R, obviously, and here I have A. Okay? Everything is fine? And this one obviously contains this hom. So this hom is containing this cyclic guy. So it has to be written in terms of the trace. So this hom is the trace of L over K times something that is in L, but is an R submodule. So what is an R submodule of L? It's a fractional ideal. That fractional ideal, we call it the complementary module. So this is the complementary module. So yes? Because these are all, A torsion free. So you have no torsion. So when you tensor with K, it's embedded. You get an embedding. Okay? Because the kernel would be torsion. Yes?
So how do we get the quotient field of R when you tensor R with K?
Sorry?
The K tensor A.
So this equality, again, you're using the fact that the dimension of R is the dimension of A, and A is another normalization. Just play with it, but the notes explains it. Okay? I mean, this has dimension 0, but it's also reduced. So it's a product of field, so it has to be necessarily that one. Okay? That's practically the idea. Okay, so we get this thing, and now how do they find our different, the Dedekind different? So this is a fractional ideal, and the Dedekind different is simply inverse. So the Dedekind different, where did I define it? Well, here is, so this is the complementary module. So dd of R over A is simply the inverse of the complementary module. So if you want, is R, so is the element of L that send the complementary module back to R. Okay? So this is the Dedekind different. The third different we needed. So these are our three different. This is the third one. And now let's observe something so we can get used to it, okay? Let's make some observation first. So the first remark that we can make right away, let me change page because my things are here, okay, is I want to express, see exactly what this complementary module is, just looking at the definition. There are elements in L. We saw that is a submodule of L. So there are X in L. They are elements of L. And what do they do with element of L? So what they are doing is that when you multiply them by the trace, okay, apply to R, they have to go to A. So X times the trace, apply to R, to any element of R, has to be contained, let me put even the ring, in A. Okay? But how does the trace apply? The trace just go inside, no? That's the way the trace works. So this is the X in L. The trace of L over K, this is a map, of X times R has to be contained in A. Okay? So this is the first important observation. What, and it's going to be very useful for us. How does it look like? Remember how the module action works, so you know this. Is exactly the trace applied to XR. Okay? And now, the second observation is that this complementary module is isomorphic. It's just a trace. The trace is just an element. So it's isomorphic to this Hom. And now I want you to think a second about what you know from commutative algebra. Okay, just go back to what you know from commutative algebra. A is not a polynomial ring, but is a power series ring. So A is Gorestan, because it's regular, no? Okay? The dimension of R is the same as the dimension of A. So this Hom, since A is Gorestan and R and A have the same dimension, is the canonical module of R. That's why you get the canonical module of R. So this is the canonical module of R. I should have to say isomorphic, because remember that there are many canonical modules, okay? This is just one possible canonical module. However, the complementary module is considered the canonical module, not just a canonical module, because it's the module of regular differential forms. So it was historically the canonical module, okay? So this is so you think just, the complementary module is a canonical module. That's all you have to think. So the Dedekind different is simply the inverse of the canonical module. Okay? That's the best way to think of it. Okay? So this is the very important. And so we can write, not by free, I'll write it here, I erase this. I erase this because I think now that we did the construction, I don't need it, hopefully. Hopefully. Anyway, you hopefully remember it. I always assume now, neither normalization, always this situation until the end, because I want to work with this, make it easier. Remember, a characteristic is always 0, so we are really in a nice situation. Okay? So what is the third observation? The third observation is that the Dedekind different then is going to also be a Hom, because it's the, it's the inverse. So it's the Hom in R, since this is isomorphic to this Hom, of so this ohm, against R. Okay? Since it's the inverse. And now the last one, this is also extremely important. In our case, A is normal. Okay? So when I go to compute the trace, even with little traces, the Li over K, okay, they are always integral in the integral closure of A over L, but they are also contained in K. So they are in the integral closure of A over L and intersect K. But that's the integral closure of A over K, but A is normal, so that's A. So this tells me that the image of this trace are all in A. So the image of the trace map, in our case, is contained in A. So this tells me that this image is already in A, so I can take x equal 1. So it tells me that 1 is in the complementary module. So in our case, you know, the trace of, because it's normal, of R is contained in A, which implies 1 is in the complementary module, which implies that R is contained in the complementary module. Should write R over A. But if R is contained in the complementary module, when I take the inverse, the inclusion flips. So this tells me that this guy is contained in R. So this is not a fractional ideal, it's an ideal. Okay? These two were clearly ideals. This was not an ideal, clearly. It was just an R sum module of L. Now this is an ideal. And we have used the normality. That's what you really need. The Dedekind different is an R ideal. Okay? So now we have an R ideal. Okay? And now what we want to do, we want to compare this R ideal, this Dedekind different with the others. Okay? That's what we want to do. All right. I have more property here about the Dedekind different, but I honestly have not time to do them. So I'll skip them, because I want to get done as much as possible of the rest. So the first thing I'm going to tell you is this. The first connection, which is important, is the connection of the Dedekind different with the conductor, which is considered an explicit approximation of the conductor. So this is going to be very important, because when we relate the difference, it's going to give us this important containment of the Jacobian inside the conductor that is used, for example, for Briançon-Skoda, is using a lot in tight closure and integral closure, in many, in Riesz algebras. So it's a very important fact. Okay? So how do we see that? This is actually easy in our case with what we prove. So we want to prove that this guy is contained in the conductor. This is the integral closure of R, obviously. Okay? So how do we prove that? So actually what we do, okay, we consider the same construction, but for R bar. So you consider the complementary module of R bar. And then you have the complementary module of R bar over A is simply the same kind of things, the Z in L, such that the trace now of Z times R bar are in A. Okay? And again, A is normal, so 1 belongs to this guy, and so in particular, R bar is inside here. Okay? So let me erase there the beginning of that. So I can write on top of that. remember that this is the complementary module. Just a trace times this guy. Okay, so we have that R bar is contained in the complementary module of R bar over A, but R is always contained in R bar. Okay? And it's easy to see, just look at the two definitions and compare it, that this is contained in the complementary module of R over A. Because you're looking at the x's, but when you multiply, R sends it in A. But if it sends R bar, it definitely sends R. Okay? So you get this inclusion. And now just take inverse. If you take inverse, you immediately get that the Dedekind of D is equal, remember this is the inverse of the complementary module, but if you take inverse here, you get R colon R bar. Okay? You're done. Because this one, sorry, containment. What did I say? Not equality. Okay? Because it flips. If this is contained, when you do, flips, exactly like we did here. The colon always flips this way. Okay? Just think about it. If you spend a second, if you not work with colon, you have to think a second, but it's not difficult to show this, but a reverse inclusion. All right. So what is the main theorem we wanted to prove? The main theorem, I have 45 minutes, almost like a lecture. What is the main theorem I want to show? I want to show the relation, okay, between these three guys I put in the board. I already explored one relation, okay, here. I want to improve this theorem. So what do I want to do with this theorem? I want to add on, okay? And what I want to show is that I take off this now, and I want to show that this guy is always contained in the Dedekind different. And we already showed that this is inside the conductor. Okay? And this inclusion we already did. This inclusion we already did. We even characterized this equality already. What we want to do, we want to also characterize this equality. And this will happen if we know that R is Comecoli. So we need even less to have equality here. Here you need a complete intersection. Here you need R Comecoli. Obviously, this is more general. Remember, this is more general because this was defined more in generally. Here we need another normalization and all that. So in that case, when you have another normalization here, this is always a flat. You just say this happens if it's a complete intersection. And here you say if happen if it's Comecoli. And this is actually a very important question in commutative algebra, is to ask necessary condition, to characterize when equality happens, when the three differences are the same. Okay? It's not always the case. For example, if R is Gorenstein, okay, then they cannot be the same. I mean, you can show that, there are several cases which we can show very easily that they cannot be the same. If you have an ideal, for example, a Gorenstein ideal, remember height-free Gorenstein ideal that define your R. Remember that an height-free Gorenstein ideal is never a complete intersection, okay, unless it's I2, perfect. And so you can prove that these guys are not the same because one is principal and the other is not. So you can prove that here you have equality here, but you never have equality here. So there are cases where you can prove that this is not the case. But for example, with Ulrich, we prove it for I2 perfect. We characterize them for Gorenstein. We characterize them for I2 perfect. They're all the same. And then we characterize when they're the same in more generality. In particular, we look at them in the case when you have a determinantal ideal. Okay? And we compare them in that case. One of the most general theorem about equality is this. R should be an almost complete intersection to have equality, so less than this, but should be also Leachin, the linkage class of a complete intersection. Okay? So Ricci and almost complete intersection definitely give you equality. Okay? So you, obviously if it's a complete intersection, they're all equal. But we are trying to see other cases, okay? And that's actually was our original intention with Ulrich, to see when they were equal and also to describe them also in terms of Gorestel linkage, which is also very important. So we wanted to explore that direction, and we have a lots of formula and then concrete formula in case of determinantal ideal. But now I'm going to go to try to prove this statement, the inclusion and this. These are the two things I want to prove, okay? And then I would like, immediately I'll give you a corollary, then I'll try to sketch these two things, okay? And then I would like to tell you the connection with the circle, okay? So let me see if I can do all that. So first, first corollary, the fact that the Jacobian is in the conductor. That we get right away. So let me erase this, and I want to tell you that the Jacobian is in the conductor. So this is the first corollary of the theorem that I want to prove, the big theorem, which I proved already pieces. Okay? So how do they fit together? Okay? So we are in the same condition now in another normalization. I want to keep that assumption, it's easier. Obviously, you could do it more in general, but I want to keep all this assumption. Okay? And then, so let me write actually better because it's a little bit more. So I have this assumption here. It's the same. So this is a complete. I don't talk about A, I don't need A. Noetherian reduced and equidimensional K algebra. Obviously, as a nether normalization, but this moment I don't take it. When we prove that the Jacobian of R over K, our Jacobian ideal, is in the conductor. So how do we prove this? That the point for this is simply the fact of expressing, to use this, what we do, so assume that these inclusions are true, okay? What we are going to do, we are going to write the Jacobian in terms of the Kähler different. But you say, here I have another normalization. And that's exactly the trick. The Jacobian is the sum of all this over all possible another normalization. Okay? But actually, you can just fix a generating set and assuming that the generating set, okay, of R over K, R is a K algebra. So you will have a generating set, x1, xn. You assume that any D of them are another normalization. And that's easy to do. Form another normalization. And now J is simply the sum over that Kähler difference. So the point, and this is written well after, is that J of R over K is the sum of the Kähler different of R over A, where A varies, over all. So where the sum varies over all another normalization of R. And actually, you don't need all normalization of R. You just need, the way you do it, you just fix, a generating set of R over K. And you assume, you can do it after, general principles show you how to do it, prime avoidance, this kind of thing. That like you do when you have an ideal generated by an element, and you can always change in the generating set, assume that any G of them form a regular sequence, okay? That's the same idea. So you can take this generating set as an algebra, change it in such a way every possible D of them give you another normalization, or a system of parameter because that's all it needs. You need to have a, so any d of them are a system of parameters for R. And you can do that, and then you take these guys, and then you get this. Because remember, this one is the d by d minor, and these are the maximal minor. But I can get the maximal minor from taking different pieces and take the, the correct thing. Okay? Is this clear? More or less. But the notes are in that one. And this gives it to you. Because this is contained in here, then the sum has to be contained, and then you get the Jacobian side. So this is the trick, and you'll have the detail in the notes. And you can also ask Matt, and today I can show you exactly in detail today how you do that, because that's interesting. Okay, so now I want to go to prove this important thing. So let's go to the proof of this. Okay. So I'm going to go to this, and I'm going to do this thing. Okay. So I think I have to erase everything, so you have to remember most of the stuff. Because now I have to erase the board. I need the board. So I'm working on this inclusion and on the quality. And again, it's a sketch, it's not a proof, okay? I will not, it's just a guide through when you can read the notes. So let me first, so if you have, in general, M and N A modules, A is any ring, okay? And let M star be the dual of M. Okay? Then there exists always a map from M star tensor N, okay, that goes to Om of Mn. And how can we define this map? You take an F, this is a map from M to A, okay, a linear map. You tensor it with an element of N, and you simply go to evaluation of F at M times N, okay? And this is well defined, all right? And in particular, this map is an isomorphism, okay, if N is finite projective. Okay? Then you can also do the composition. You can start from M tensor N over A, okay, take the natural map that sends you to the double dual, which doesn't have to be the same unless it's reflexive, tensor with N over A, okay? And then this one with the same map here, this is the dual of M star. So this is Om A of M star against N. And you can compose this map from here to here. And this map, if you compose it, what it is, it goes from M tensor N, it sends it simply to, you take an F here, because this is going to be an F, okay, in M star, and F, you have to send it to F of M times N, okay? Because this is a map between the map here to N. And this one is also an isomorphism if M is reflexive and N is finite projective. Which is clear, because if M is reflexive, this 2 is an isomorphism. And this is an isomorphism by this, because it's finite and projective. Okay? So reflexivity gives you this isomorphism, and finite projective gives you this isomorphism. So the composition is an isomorphism. So now we are going to apply this picture to the case where R is an A algebra. So our case, actually, A is another normalization. And all this module, M of n, are simply the ring R. Okay? So just apply this picture to this case. And let's see what we get. I'm going to make a big diagram. A big diagram with lots of colors. First they're going to be white, but then I'll put colors inside. So first of all, what does the diagram I want does? So I start with, remember M and N are R. So I have R tensor R over A. Who is this guy? Enveloping algebra, which we have used so much. And enveloping algebra goes to this guy. Let's see what this guy is. This guy is the hom of M star. But M star is hom of R over A, okay, in A, against R, because N is R. Okay? And this is this composition. Okay? Call it, I don't know how you want to call it. You can call it big phi, this map. Okay? And these obviously are all RB modules. Right? Now, very important. Inside here, there is an annihilator of D. The guy that is going to be my another when I push it to R. Okay, so I really care about him. And notice what this, how can I characterize this thing? What is this thing? If you didn't think about it before, is the U in the enveloping algebra such that annihilates the element of D. So such that U x tensor 1 is equal to 1 tensor x. Actually, this is here, so I have to multiply this way. So let me write it this way. It's better. X tensor 1 with U is 1 tensor x times U. Okay? So this is exactly the guys that makes multiplication commuting. Did I write the same thing? Yeah, that's correct. Okay. So this is the largest submodule where the two R module structure coincide. Multiplication on the first is equal multiplication on the second. Okay? So we talked a lot about this two R module structure before, and this is exactly the largest where these are the same. Now, you can look inside here. I should have used already the color. I didn't, but I start now. And you can look at somebody else where the same thing is true for this guy. And this is the hom on R of A of RA against R. So instead to take the A, obviously you take only R linear map. These are particular A linear maps, so you have a containment. And if you write this well, you'll see that this is exactly the same as this. It's the largest RR submodules where the structure are the same. So we have an identification among these two, and that gives us a map induced by that. So let me call it like this, because it's induced by that map. Okay? So this is included here, and you have an induced map because of this, because they are the same thing. They are characterized as the largest submodule where the structure becomes the same. And the theorem let's say, a very important theorem that we need at this point, okay, is the fact that, let me put it this way, this thing is an isomorphism. In V theory, I need this assumption. But I can just assume that R is Comecoli. Why? If you have another normalization, what does it mean to be Comecoli? It means to be free, free over A. So all these assumptions are going to be true. R is a free A module. So it's obviously reflexive, it's always projective. Remember that when you have another normalization, R is Comecoli, if and only if R is A free. So everything is true. So if R is Comecoli, this is an isomorphism. So this is an isomorphism if R is Comecoli, because this is an isomorphism as well. They're all isomorphisms. Okay? Okay. So we have this beautiful picture with two isomorphisms for R Comecoli. Now I still have to even prove the inclusion. I didn't prove the inclusion. But the isomorphism is going to be very important to prove the quality as well when R is Comecoli. So now what we're going to do, there is a crucial lemma that I cannot prove, but it's very important, but the proof is there. And the crucial lemma says the following. So I'll have to give you some. So I'll state it and then explain what things are and tell you what really means. And then all this will be a trivial corollary of the crucial lemma. So the crucial lemma says the following. Maybe I do it in yellow because this color is not very visible. Okay? So again, you have assume that R is Comecoli. You start from the annihilator of D, okay? And you want to compute the different, the nether different. So how to compute the nether different? You apply mu to it. So it's mu restricted to this guy. Goes to R, its image, remember, is exactly the guy we want. And what the lemma says is that this is Comecoli. You can factor this map. And you can first go to the isomorphism there, the script phi, okay, which is the remember, this is an isomorphism if R is Comecoli, A of RA. So you can first go here, and then you can go down here, okay? And which way do you go down here? You apply the evaluation map to the trace of R over A. And you're going to tell me, so you evaluate, so the trace is an element here, and you simply evaluate it. And then you get an element in R. So what is the trace? And how do I think about the trace inside here? These are not filled. So I tell you how you think the trace. If R is Comecoli, R is free. So R is going to be A to some power. I don't know which letter to use. R, whatever. Okay? It's free. It's a free A module. Okay? And now, take any element, X in R. It gives you multiplication, okay, from R to R. Think of R as A to the R. You can write this multiplication as a matrix. This is a multiplication with is a matrix with entries in A. Take the trace. So the trace from R over A is a map from R to A that simply is the trace for every element X, associate the trace of mu of X. Okay? That's all. and give you a map from R to A. So this is definitely an element in home. It's a very linear map, so it's an element here. So this trace is an element here. You evaluate it, and you get an element in R. Okay? And this says that the theorem says that this commutes. That's a crucial lemma, which I'm not going to prove. And now, once you have this theorem, we can prove everything. So let me prove immediately what I wrote there. Okay? So I'm going to erase now this, even what I plan to prove. Maybe this I can erase. Yes, maybe I can erase this. Though you have to be careful because you're going to need some of this. I'm going to need this. So let me erase this, so it's going to be easiest. And I'm going to work on this diagram. I have to rewrite this diagram. That's the point. The diagram that I just erased, I have to rewrite it. So this is the proof of this inclusion and equality. Okay? So let's do it. And it's due to nature. Okay, the proof works this way. So you apply the crucial lemma to K, which is the quotient of A, which goes to L, which is the quotient of R. Remember, K is contained in L. And we get this diagram. The annihilator of dL over K, okay, over LE is isomorphic. These are fields, so everything is free, so everything is come equally. I mean, this is not a field, but this is free over this, so there is no problem. So you get this guy R over K, the vector space, so it's obviously free over K. And this, you have equality, because if you remember, this hom is L times the trace. We saw that before, the trace of L over K in L, and then you go to L with evaluation of the trace map. Okay? So you have this long diagram. And you consider the map, the composition map, okay, that goes from here all the way here, and call it mu. It goes from the annihilator back to L, just composing. Under here, I have the annihilator now in R idiot D, which is the guy I need, okay, D of R over A. Usually I just call it E, but it's a different D, so I have to put it like this. And there is obviously a map here. And now here, this corresponds to the phi map, the one I call script phi, the one that, this one, that is an isomorphism only if you have a comecoliness. In general, it's not an isomorphism, okay? And here you have the in R, exactly the guy here. In A, RA against R. So this is this map. Okay? And then you have equality again here, because who is this guy? It's a complementary module times the trace. Here you have a map. We have seen this before. And here you have, instead to have L is all L, you have only a submodule, which is the complementary module. Remember, this is included. That's how we define the complementary module. Okay? So you have a map here. This is actually an inclusion, okay? And then here you have an isomorphism because this is exactly, remember, the Dedekind different of R over A. The inverse of this. This is R, not L. The inverse of this is exactly Dedekind different. We have seen this before. The hom, one of the corollary, the hom of this in this is the Dedekind different. Okay? That's how I can think of the Dedekind different. And so now, what I want to do is that this diagram, which is commuted, everything commutes, Okay? This is also included in L, obviously. Shows you that the composition of the maps in this row is, so, is mu applied to this guy, because the same map is mu. So mu goes to finish here, obviously, because the composition goes to finish here. But this is exactly the nether different. And when do I have equality? I have equality when this is an isomorphism. And that's true if R is Comecoli. Okay? So this finish a sketch, the more detail in the thing, the fact that we have an inclusion and Comecoliness. Obviously, there are lots of facts here that I hide. And now I have 15 minutes, 17 minutes, and I would like to talk about the relation with the Sokol, okay, in this left 15 minutes. And as I said, you can read all this stuff you can read with the details in the notes, but at least you have an idea what to look for and what's the important thing. Here, the important thing is really this map and this connection of this as the largest submodule where everything becomes the same structure. Okay? That's really what makes everything works. Now I first want a corollary, and then I can do the connection with the Sokol. I need a corollary, and then I do the connection with the Sokol. So the corollary is as following. Obviously, you can also prove what I told you last time, that this guy is not here anymore, but the Dedekind different is a mixed and even characterize is how does it look like and what what is minimal prime, what is you can write it as an intersection of height1 prime component of the nether difference. So you can do a lot of this other thing, analyzation, that I have not time to do, but some of it are in the notes, some if you're more interesting. Some are in Unique and Swanson, but most of the stuff is in Kuhn's. So you have to go through Kuhn's books to find all this stuff. It's not easy and they're in German, but there is a lot of this thing that are quite interesting, actually, that I didn't have time to talk about, obviously. So assume now that R is an I algebra, and R is Comecoli. Also assume that the hom is cyclic as an R module. And then what you can get, I'm not proving it, but what you can get, just go through it, is that R times the trace of R over A is the nether different of R over A times the hom of R over A. So in this case, I'm not assuming that I have another normalization and all that. That's important. It's much more general, but it does use this definition of trace, because you still have an A algebra, you assume it's Comecoli, and you can still think about the trace in that way. So you can, you want to apply the crucial lemma, but the crucial lemma did not need that A was another normalization, it just needed that the map is finite. So you want to be in that case, okay? And you have it because this is cyclic, so you can get, the detail are here. But I need this to talk about the Sokol. But I wanted to do it in general when I may not even have the another normalization. I don't want to be in that situation now. I mean, I have another normalization, but I don't want to assume that. So I want to be more in general case. So I look at now I assume that R is Artinian. Okay? So it's a local K algebra and is Artinian. Okay? Now, if you have any R module, what is the socle? Okay? What's the socle of M? We call it soc M. Okay? The socle of M is the largest K submodule, okay, K vector space contained in M. So if you want a 0 column, the maximal ideal is the maximal ideal in M. Okay? If you want, you can also write it as hom of Km in R. Okay? And it's easy to show that the socle is non-empty, so the socle of M is non-empty if and only if M is an associated prime. Okay? And now, and not only if M is Artinian, M is different from 0 if and only if the socle is different from 0. That's actually extremely useful, can be used a lot of time to show that something is 0. So if M is Artinian, so the socle is very important. M is different from 0 if and only if the socle of M is different from 0. You have to think about the socle as the dual of the generator for the module. So the generator for the module are extremely important. You know very well. You want the generator to understand the module, like for an ideal. Okay? And think about the socle as the dual of it. It really gives you so many information about the module as well. Okay? So now what we want to characterize what the socle is for a complete intersection. This is obviously a classical theorem, okay? But it's very important. And in general, we want for R Gorestan a relation from the socle and our difference. And the theorem is as following. So we are in this situation. R is a local K algebra. Remember, I am in characteristic 0. K is a field, is Artinian, so the dimension of R over K is finite. Okay? And then first, if R is Gorestan, the socle of R is exactly the Nader difference. And you have this in one of your homework, again, it's homework 4. We'll ask you to do this kind of thing, to relate it. I think, no, maybe just relate the Jacobian. And then Tate, this is due to Tate theorem, but its proof is much harder. If R is a complete intersection, then the socle of R is the Nader different, but is also equal to the Kähler difference. And you know the quality already. We have proved the quality. If it's a complete intersection, we have the quality. So everything follows. If it's a complete intersection, you already know this equality. Okay, so I only have to prove A. If I prove A, I'm done, because B is obvious by what we proved before. So we only have to show A. And then I want to show the connection with the Jacobian determinant, okay, which is also in your notes, and it should be clear from what I did before. So I'm going to erase this now. I need the corollary. Okay, so I only have to prove the first claim. And so R is Gorestan, so it's isomorphic to his own canonical module. And I can write the canonical module as an home of R against K, because K is also Goresten, and this is Artinian. So this is the canonical module. Okay? And now, so we want to talk about the socle of R, but then I can just compute the socle of this home. So it's enough to show that the socle of home of KRK, okay, is equal to the nodal difference of R over K times this home. Because if this is true, then this is generated also by the nodal difference. Okay? But now look at the corollary. The corollary exactly describes this guy. And it tells me that this guy is the trace times R. So this guy, by the corollary, that's why we use the corollary, is R times the trace of R over K. So I have to show this equality. And it's enough to show two things. First of all, that the trace is non-zero, okay? And then the trace is in the socle. Then, since this is principal, because obviously it's isomorphic to R, okay, this is going to be principal because it's Goresten, it has to be generated by the trace. So I have to show this one, let me call it A, and B, that the trace is inside the socle. And I'll be done. So I have to show these two things. Trace is different from 0 and trace is in the socle. Okay, but the trace is non-zero because remember how I defined the trace. It's the trace of multiplication. Look at the trace of the element 1 in R. It's the trace of the identity. But the multiplication, the identity, the trace is just the dimension, the vector space dimension. So this is just the vector space dimension of R over K, which is different from 0. Okay? So the trace, because we are in characteristic 0. So the trace, is different from 0. So 1 is done. And now we have to show that the trace is in the socle. So take an X in M, in the maximal ideal. Okay? You want to show that X times the trace is 0. And now take any Y in R and look at X times the trace. Okay? You want to show that this is 0 to show it's in the socle. But this is the trace of xy, which is the trace of the multiplication times xy. And now this endomorphism, okay, is nilpotent because the maximal ideal, the power of the maximal ideal is 0 because the ring is Artinian. So this tells me that this trace is 0, and I'm done. The trace of an nilpotent endomorphism is always 0. So we are done. So we prove this one, and I have 5 minutes. So I'm very happy. Maybe I went too fast. I'm sure I went too fast. But I do have 5 minutes, which I'm very happy because I can, thank everybody, and I can show you the connection with the socle. So in this case, all right, in this situation, the situation of Chu, so I'm in this situation. What does it tell me that R is a complete intersection? It's simply the fact that you can write your ring. Remember, R is Artinian, is a complete intersection. Another is a local K algebra, so you can write it and this is a complete intersection, okay? And so now, when you go to compute all this object, remember you want to look at the annihilator, you want to look at the socle, which is f1ft colon x1 xt. This is the maximal ideal over f1ft. But we computed this at the beginning of this lecture. This is a regular sequence inside a regular sequence. I told you that this is an Orcott ideal. And I told you, how do you compute this column? You have to write a transition matrix. So you have to write f1 ft in function of x1 xt, so you write it as x1 xt times a matrix. But which matrix is this? This is exactly the Jacobian matrix. It's like doing the derivative of these guys. So this is the Jacobian matrix. You're doing the derivative, okay? That's how you write f1 ft in terms of x1 xt. They just take the partial derivative and characteristic 0. And then you can see immediately, you have to be careful to the coefficient, but that's practically what it is. This is a Jacobian matrix, the transition matrix. You can really write it as this way, okay? And now what's happened is, by what I told you about Norcott ideal, this guy is simply given by the determinant of this matrix. The determinant, the f divide f. So the circle is simply, in this case, given by the Jacobian. And this is the Jacobian ideal, because remember that in this case, the dimension of R is 0. So the minor that you have to take are exactly the only possible, which is the maximal minor. Okay? Is this clear? So the circle, this is a square matrix, because this way have exactly D and D, and its determinant is the Jacobian ideal, and its determinant is exactly the circle. You can generalize this story, okay? And that's done by Eisenbach and Ulrich, but it's much more complicated, okay? You can look at this when the dimension is higher, you can still talk about what would happen there, and you can define in a certain sense circle and see what's happening in this case, and also when it's not a complete intersection, but you need a lot of assumptions. Okay, so I'm going to stop here, and in my last 1 minute, I want to give a big, big applause to the organizer and to CMAT, and above all, to Jack and Jonathan to think about Pascal already many years ago, but also to the local organizer. And Eureka, where is she? Maybe she's not here. Yes, that have done so much for us, and they have been so marvelous. So, and thank to the audience, because without you, there is no conference. So thank you to have come and to have listened and to be patient, even when one goes too fast and doesn't show all the proofs. So thank you so much. And the TAs. Matt, thank you so much. And all the TAs, okay? Thank you, guys. I hope you have enjoyed this experience as much as I did. Thank you. I'm going to clean up the notes and then give you a version, and I may find more typos, and then I send a better version later on through Jack, but I'll work to simplify typos this afternoon and then send you a version through Jack. Okay, thank you so much.
You're welcome, and thank you to you for your wonderful course with all these beautiful and interesting mathematics. It was very inspiring and encouraging with all these conjectures, relations, and everything. So thank you, Claudia. Are there any questions for Claudia?
But you can ask any question later. You can find me always around the building, okay?
Okay, then thank you again, Claudia.